Good morning, everybody. I'm Suma Momudu, and I have the pleasure to present to you downloading and streaming data from Sandbox to QGIS. First of all, we'll have an overview of Digital Earth Africa. My colleagues have already made some presentation on Digital Africa, but we have to consider the data storage that now we host. Digital Earth Africa hosts a variety of data products on the platform of Amazon S3 for public access, free public access. It is also an exploration tool enabling users to browse product Sandbox Explorer. You can also have metadata access. The Sandbox Explorer includes a spatio-temporal asset catalog, the STAC, which is an endpoint for easy metadata searching. You have the link. And we have also the benefits of the spatio-temporal asset catalog, which is a standardized geospatial description which facilitates a quick identification of data by product, location, or time period for efficient download and streaming into GIS software. An overview of STAC, the Spatio-Temporal Asset Catalog. STAC is a new specification for describing geospatial information, facilitating easier indexing and discovery of data. The functionality of STAC through the Digital Earth Africa metadata enable quick identification of available data based on product, location, or time period. The usage. These metadata support efficient downloading of data to local storage or direct streaming into desktop GIS software like QGIS. This notebook provides a brief introduction on how to access and use Digital Earth Africa STAC metadata, how to construct a STAC metadata API call, how to search for STAC metadata and load the result into Python, how to inspect and plot the unique STAC item contained in the metadata, how to inspect asset contained within a STAC item, how to download data using STAC metadata, and how to stream data into QGIS using STAC metadata without downloading it first. The approach for executing this notebook, first we have to load packages that will be necessary to carry out the processing. We have to connect to the data cube. We search the STAC metadata. During the searching of that STAC metadata, we have to construct the STAC API call, load the STAC metadata, followed after by inspecting the STAC items, inspecting the assets, downloading files using the STACs, and finally streaming the data into QGIS. The loading of the packages. The language used in the platform is Python, so we have to import Python packages that will be used for the analysis. So We have to force GeoPanda to use Shapely instead of PyGeos. And in a future release, GeoPanda will be switched to using Shapely by default. You have to import the os.environment, use PyGeos, import DataCube that will enable you to have access to the catalog of imagery, import the URL lib.request, JSON, import the GeoPandas as GPD, import RioXArray, import odc.aws from pprint import pprint from datacube.testutils.io import rio underscore slurp underscore xarray. The next stage is to connect to the DataCube. DataCube, you have the script equal datacube.datacube in bracket app equal downloading underscore data with STAC. Searching stack metadata. First, construction of the stack APL call. We need to set up some analysis parameters that will be used to search for metadata. These include product, which is the same product name used to load data directly using the dc.load. In this example, we'll choose a small area of Ile-Ife, located in Osun State, Nigeria. If you need the full list of available products, you have to browse the Digital Earth Africa Sandbox Explorer. So the script to retrieve the data we need is product equal sentinel2 underscore L2A. We indicate the start time 2020 January 1st, and the end time is 2020 January 31st. The B box will give the coordinate 7.65, 4.35, and 7.40, 4.70. These are the coordinates for the coverage of the area of interest. We can now combine the parameters above to create a URL that will be used to query Digital Earth Africa's stack metadata. The metadata can be previewed in another tab by clicking the URL. So we have the script below, root underscore URL, https // explorer.digitalearth.africa// stack underscore URL, and we have the root URL, the search collection, product, we indicate the product and time, start time, end time, and VBox as defined earlier. And we have to print, we ask the system to print the stack URL. What you have below as HTTPS and Digital Earth Africa start search collection is the Sentinel-2 L2. The time period, you have the beginning and the end time, 2020 January 1st and 2020 January 31st, and the coordinate of the study area. We load the stack metadata. We can now load the metadata from the URL. The stack metadata is stored in JSON format, which we can read into nested Python dictionaries using the JSON Python module that is indicated as with URL lib.request.url open stack underscore URL as URL. Data equal JSON.load URL.read in bracket, decode in bracket, and we close the bracket. Pprint data depth equal 1. And you have the result of that script, which give you the context, the features, the links, the number match, the number return, and the type of data, which are the features collection. We inspect now the stacked items. From the input above, the number return value indicate our search return 6 unique results. These results are known as stacked items. These are an atomic collection of inseparable data and metadata, such as a unique satellite data. For your information here, the number returned will vary accordingly to your study area. Here we have the number concerning our study area. The data for each stacked item is contained in the metadata list of features. When we type the pprint data features depth equal to, we have the output of the printing, where you have the asset, the V-box, the collection, to give you the product you are using, the geometry, the links, the properties, the stack version, the type features, the geometry, and so on and so forth. This output was truncated and viewed as a scrollable in element or open in a text editor. You can adjust the cell output setting. Inspecting the stack item. The stack features are stored as GJSON, a widely used file format for storing geospatial vector data. You can easily convert it to a shapefile to a spatial object using the GeoPandas Python module. This allowed us to plot and inspect the spatial extent of our data. The comment here is convert to features to a geodata frame. The script is GDF equal gpd.geodataframe.from_features data features. We comment here, plot the footprints of each data set, and we define the GDF plots. We indicate the size, and we indicate also the edge colors. We print the geodata frame, and we can see that it contains useful metadata fields that provide information about each data set. GDF.head in bracket 1, we have the geometry, we have the title, you have the geometry here, you have a polygon, you have the title here that give you the indication about the product, you have the GSD, the ground sampling, and you have the projection, the EPG, you have the platform, is Sentinel-2, the view of Nadir, and the instrument is the multispectral instrument. We can use this to learn more about our data. We can plot our data set using the EO:cloud_cover field to show what percent of each data set was obscured by cloud. The yellow color indicates a high cloud cover, and it is indicated for using satellite imagery or Earth observation in the optical range that the cloud cover should not be more than 90%. So here we have a comment on the color features by cloud cover, gdf.plot in bracket colon equal EO:cloud_cover. We give the coloration of the map, viridis, we give the alpha equal 0.8, and we give the edge of the colors, black, and the legend true. What's what we have in this area. And you have the legend here that give the cloud cover on this area. So our image vary here between 0 to almost 40, 30, 35 on the cloud cover. That indicates that you have images that are not yet on the level of high cloud cover. Inspecting the assets. Each stack item listed in features can contain multiple assets. The asset represents unique data file or layers, for example, individual remote sensing bands. For Digital Earth Africa Sentinel-2 product, these can include the band metadata, etc. So we make the script stack_item data features and we do pprint stack item asset gets equal 1. You have here the result of the script that give you all the bands available, the information, the metadata, and overview, the thumbnail, and the visual. Each asset, for example, the band 5, will provide a unique URL that can be used to access or download the data. In this case, the S3 prefix indicates our data is stored in the cloud on Amazon S3. Using the pprint stack item asset B5, we have here the Earth observation bands. You have the name of the bands. You have the URL here. You have the projection 32632. You have the projection for the image. You have the projection transformation. You have the role, the title of the image, and the type is an image in the format TIFF. Now downloading the files using the stack. Now that we have the URL, we can use this to download data to our local disk. For example, we may want to download data for the B5 satellite band in our stack item. We can do this using the S3_download function from the odc.aws. In the comment here is get the URL and then download. The URL is here, URL equals stack_item asset B5, and you have the URL odc.aws s3_download in bracket URL. The result gives us here the bo5.tiff. To verify that this file downloaded correctly, we can load it into our notebook as an xarray.dataset using the rayo xarray.open_rasterio. In the comment here, we put load data as an xarray.dataset, download_ds equal rio xarray.open_rio rasterio in bracket the band we are interested to visualize. The comment here give plot a small subset of the data, downloaded_ds.icell, and we put in bracket the x slice, we put the dimension, the y dimension, and we plot and we give progress equal true. This is the result of our subset of our area we wanted to download. It's not the full area, but a subset of it. If this notebook is being run on the Digital Earth Sandbox, the save file will appear in the frequently used code directory in the Jupyter Lab file browser. To save it to your local PC, you right-click on the file and click Download. If you want to download multiple files from the B5 band for each of these 6 stack items written by our search, you have the URL get the list. We have the URL to scripts. We download each URL. To download all available bands, example, the iset for a single stack item, you have also the script that is here, stack_item. You define the URL, and for downloading each URL, for the URL in URLs, print URLs odc.aws.s3_download URL. Now we are streaming the satellite data. The challenge is downloading large satellite dataset directly to your own local disk can be slow and time consuming. Many of you have faced this challenge. The solution is streaming data directly from the cloud, which can be more efficient, especially for cloud optimized GeoTIFF format, COG, which allow for streaming small image chunk at a time. What's happened here is from the cloud, your image will be split in different small images that will now be downloaded and reconstructed in the environment of work. The implementation, this section will demonstrate how to stream data directly into the QGIS software we have chosen. The first step is to convert the Amazon S3 URL into HTTPS format so that it can be read more easily. We have the script, get the URL, get HTTPS URL, and we have the get HTTPS URL. All these elements are in the script. We have now the results of what we have requested, and we have the different HTTPS for the band 3, for the band 4, and for the band 5. Now we are streaming the data into our software, QGIS. To stream the data directly into a GIS software like QGIS, without having to download it, first select and copy the HTTPS URL above to your clipboard. And then you open the QGIS, and in QGIS, you click layer, and add raster layer. You have the procedure here. You go open your QGIS. Normally, you have already installed QGIS in your laptop. You open your QGIS, new project, and you go to layer, add layer. From add layer, you go to add raster layer. On the data source manager, raster dialog, click the protocol here. You are here in the data source manager. You click the button here for protocol, HTTPS, and in protocol, you ensure that this HTTP//HTTPS/FTP is visible, and you paste your URL you have collected from your script. And you have here the link, the URL that is indicated for the band 05.tif. You click add as usual, and you close. And after a few moments, you will have your image displayed on your workspace. You click now on raster on the main menu, and in the drop-down window, you click on miscellaneous and build a virtual raster. What you have here, in this visual raster, miscellaneous, and build virtual raster. The procedure will be given to you, and you will have the opportunity to try this exercise, choosing your own area of interest. But first of all, you use the area that has been provided to you. On the new window, you click on the Parameters tab, and clicking on the Parameters tab, you click on the button of Input Layer. What you have here on the Build Virtual Raster window that appears, you have the parameters here, and you will put the input layer. You define the specification, place each input file into a separate band, and you execute what you have. The selected layers to be used for the color composite, because you want to visualize your image in a color composition. So you put the band accordingly to the red, green, and blue. You have the B5, B4, and B3 following the order on the open window, and you validate on OK. And you place each input file into a separate band, like we said earlier, and you keep the default, and you run your request. A log tab will show the level of progress. And after the completion, you will have your virtual image. This is the log tab that will give you information about the progress. You have the bar of progress here. And at the end of the processing, you will have your color composite that will display on your workspace. That's how we carry out downloading and streaming our data into QGIS. Thank you very much for your attention. I have to acknowledge our ecosystem builders, as mentioned by my predecessor. There are many to list. We have also to thank the Australian government and the Helmsley Charitable Trust. Thank you for your attention. Together, let's unlock the promises of tomorrow. For other contacts, you have the link info@digitalthreatafrica.org. Thank you very much.
All right. Thank you, Mr. Suma, for this presentation. Before we go to the next presentation, which will be anchored by still Mr. Suma, there are some questions or inquiries in the chat that I want us to attend to quickly. I don't know if we are already attending to them, Mr. Adim. Are we attending to them, or do we allow them to express it, to express those questions loudly here? Maybe some of them.
We are
I
trying
can
to
see.
attend to them now. If there's anyone that
Okay.
wants to say it loudly. Apart from that, please, I don't know if Mr. Suma can share the Sunbox account platform
All right.
showing the notebook that we could
Okay.
see cells that are running and have an idea of what is going on. This will enable participants to have a clear view, and then they will be able to practice it at the end of the session. Mr. Suma, is it possible to have something like that?
Yeah, the sharing of the notebook. Okay, well, maybe while that is on, let's see other question on the chat. Can we have these steps outlined for future reference? Definitely that will be in the notebook. The steps are there. I saw one question. Mr. Suma, please, where did you get the build virtual raster window? Can we try to attempt to that? There are some other observations also. The Jupyter page is blank from my end, please. There remains that most of these things will sync with time. Okay, that's just an observation. Do we open the default environment for this session?
We can use the default environment.
Yeah.
The notebook that has been presented. The notebook that has been presented will be shared also, so that you all test it at your own end using the region of interest of your choice.
Okay, Mr. Sumari is saying, I would like to have more clarification about the URL creation. I think we need to come back on that.
Yes, Mr. Suma is going to share his
Okay.
platform so that we could quickly view the notebook.
Live.
Are you hearing me? Hello? Are you hearing me?
Yes, we can hear you now.
Okay. For the question related to where did I get the build virtual raster, I'm displaying it here. We are here in the streaming into QGIS, and we said in the raster, you click the drop-down list, and you will see miscellaneous. And in miscellaneous, you will see build virtual raster. I will go now and present the notebook for the participant to see how it was carried out in the notebook. I will go on it and you will see what to do on. Good morning and welcome back. This was the topic of our presentation just now. You are here in the environment. I will return this is what was presented earlier for the notebook. To gain space, I've closed my down folders, table of contents. The exercise, the notebook, downloading and streaming data using STAC metadata. The product we are using was the Sentinel-2. And these were the element we consider for preparing the STAC. We are here at the getting started. And the first stage we said was to load the packages. For the script to run perfectly, there are some Python packages that need to be loaded, and we have defined them here. In this hash, we are making comment on what we intend to do, and we have here to import the OS, and we define them using the PyGeos. We import the data cube and so on and so forth. We have them all here. The next operation we did was to connect to the data cube, and we put it as script here. That's what we have, downloading using the downloading data underscore with stack. On the searching of the stack metadata, construction of the stack API call, we have here, like I showed in the presentation, the product S2L2A. We have the starting date and we have the end date, January 1st, 2020 and January 31st, January 2020. The root URL is defined here, HTTPS, and the stack URL is also defined here in the script. And below, we have the URL that we requested for. We load the stack metadata with the URL lib.request URL open stack underscore URL. For your information, the notebook is ready-made for the users to exploit. What matters most is when you are defining those using the notebook, you have to indicate here on B box the coordinates of your study area. You have the product you want to use, you have your starting time date, you have your end time date, and you have here your coordinates. GIS is related, or the data are spatial data, so you should have your location. And it will show later. You load the stack metadata. That's what we did in this cell with the URL lib.request, URL open, stack underscore URL as URL. All these features will give you this information that you have, and you have the number returned that is here, 6. This is the number of elements we have, and after we inspect the stack item, in this cell here, we requested the pprint data features, and it gives us all this information based on our request. That's what we have here. We convert the features to a geodata frame. That's what we write here. And we plot the footprint of each data set. We define how it should be presented. We got the GDF, the geodata frame, where we have the definition of the geometry, polygon. You have the title, you have the GSD. The GSD here is your ground sampling distance. It is equal to 10 here. You have your projection, you have the platform, your off-nadir view, and the instrument that was used. You have the remaining information from instrument. You have the cloud cover, you have the file format, and you have the region code, and the date at which it was created. So these are the metadata, and the metadata are the information about your data. Now we define here the cloud features, color feature by the cloud cover, and this gives us the information on the level of saturation of the image by cloud. And we know that it is lesser than 40. That means we don't have too much cloud in our image. By principle or by rule, your image should not have more than 10% of cloud cover. The stack item here is defined, and we now have all the band from B1 to B12 that enable us to now do all the composition we want to do, or the operation we want to do. We will define now the pprint stack item asset for the B5, and it gives us these properties: the band, the href, that is the URL. We have the projection defined, you have the shape, you have the transform, you have the role and the title of the band B5, and the type. It is an image in the format of TIFF. You download the file using the stack, and you get the URL. For your information, all the cell here, where you see a number, indicate that the cell has been run. And to run the cell, this is where you have to click, run this cell and advance. When the cell is running, you will see an asterisk. And when the cell is completed, a figure will appear. That is here, the number 12. You have the result of this number 12 cell that give you bo5.tif. You have also the load data as an X-array dataset, and from there you have defined the dimension of representation, and we have here our band that show a portion of the area of interest. That's why we have different coloration, and from the deep purple to the deep yellow, it gives us the features you have on the ground. And based on the features you have on the ground, you can do a visual interpretation to identify the settlement, the roads, the vegetation, and the water body. We download here multiple files and we get the URL as indicated for it. Now we will do the streaming without downloading. And for that, we have here the script. You indicate the asset, the band file, the URL, and we have the list of the band we want to use for our color combination, B3, B4, and B5. And we get the URL for those bands, and we have them here. The first band, B3, the second band, B4, and the third band, B5. We stream the data into Python, and we have this result of what we indicated earlier. We do a reproduction of and load the data from the data cube, where we indicate this ds equal dc dot load product, and we indicate here the product, which is sentinel2 underscore L2. We indicate the time period, the starting time and the end time, January 1st, 2020 and 31st January 2020. We indicate here the dimension of representation. We indicate the resolution. We indicate the output CRS, that is the coordinate reference system, and the task churn. We will have here our elements that give us information about what we requested. We load the data as an xarray.dataset. And from there now we come to our QGIS. And like we indicated, we don't want to send it straight into the QGIS, but we use this approach, layer, add layer. And when you click on add layer, you have add raster layer, because you have the option of which type of layer you want to use. And your satellite image is a satellite data. So you use add raster layer. After using that raster layer, you go to the data source manager. In your data source manager, raster, you click on protocol here, the button, radio button for protocol, which is selected. In protocol, you select the HTTP, HTTPS, this format of type for the protocol, and you paste your URL. This is for the band file that it will add to your image, to your platform, and you click on close. When you add it, it will display on this your image, and this is the procedure we have chosen for this streaming on QGIS. Thank you very much. I just want to, the notebook was earlier run. For those who want to redo the streaming, you come here to kernel, and we said restart kernel and clear output of all cell. And when I do this, I click on restart, you will find out that all the operations have been cleared. You see the bracket here is empty. So it is left to you to now customize this notebook to fit your area of interest. These parameters remain as they are. And if I want to run this first cell, I click on the cell and I click on run. You will see that the number 1 has shown, and you do as for the next cell. In preparing your notebook also, or using your notebook, you should have also the concept map of what you want to do to fit accordingly to this notebook, and you adapt it accordingly. You define the type of product you want to use, the period you want to set your range of study, and you define your coordinate. Thank you very much.